Hello, everybody. Good morning and good evening. It's a pleasure for me to introduce the invited speakers of this second day of CAR 2022. So let me start with Professor Jarosław Grytczuk. It's a pleasure for me to introduce Jarek. And if you don't meet Jarek, it is very easy to find Jarek in a conference. You only have to look for a group of young people and that is follows someone, and this is Jarek, like Aristoteles in the old time. So Jarek is a very musical, coloring, and dynamic mathematician in many sense. So thank you, Jarek, to be here.
Thank you.
The time is yours.
Thank you very much for this very kind introduction. And I'm glad to be here, to have this opportunity. Thank you for the invitation. I will start sharing my screen, and I will start to present the topic. I hope you will see it in a while.
Yes, we can see.
Okay. So I will say a bit about one of my favorite topics, one connected with coloring. So let me just start with introducing basic notions and state some problems. Okay. So let me start with explaining what good and what bad may happen when we color a graph. So suppose we are given some finite graph, and we color the vertices of a graph by just two colors, say yellow and blue. And in any such coloring, there will be bad edges and good edges. So bad edges, as you can imagine, are monochromatic edges. I mean, the edges whose ends are colored by the same color. And this is because in a proper coloring, we wish to have only good edges, meaning that the ends of every edge are colored differently. So good edges are edges colored non-monochromatically. So this is just a terminology. In any two coloring of the vertices of any graph, we have some good and some bad edges. And now we can make a definition of a vertex saying when a vertex is happy. So a vertex is happy if it has at least good edges as bad edges among the edges incident to that vertex. So for instance, in this example, for instance, this vertex is, I guess, non-happy because it has three bad edges and only one good edge. So 3 is more than 1, so he is not happy. But that vertex is happy because there are 2 good edges and only 1 bad edge incident to that vertex. Oh, I have a picture where I just put some smiling faces on happy vertices. So I hope you understand this definition. And majority coloring, as it is called, is a coloring in which every vertex is happy. So this needn't be a proper coloring, but of course, proper coloring is that every vertex is very, very happy. There are no bad edges at all. But we are trying in this problem to make this happiness, say, 50-50 at least for every vertex. So in this example, it is still not good situation because we see some unhappy vertices. But what can we do about it? Well, so here is an old result by Lovaas that was formulated originally in some different way, but this result says exactly that every finite graph can be happily colored, has a majority coloring by just 2 colors. So we still can make all vertices happy with just 2 colors. How to do it? Let me show you the simple argument for that. And the argument goes as follows. If we have some unhappy vertex, like here in this example, we can just switch its color to the other color. We have 2 colors, so we can switch a color of an unhappy vertex to the other color. And let's see what happens. So I summarized this procedure by just saying that we are finding a coloring that maximizes the total number of good edges, because when we switch a color of unhappy vertex, the situation changes in the neighborhood of this vertex for the edges incident to that vertex. Yes, every edge that was bad becomes good, and good edge becomes bad. But now this vertex is happy because the number of good edges increased. That vertex is unhappy, but we can still do something about it. So we can switch its color and make it happy. So in every such switching step, the total number of good edges increases, but the process cannot go on ad infinitum. So at some point it must stop, and at this point we have the maximum number of good edges in the total, and all vertices must be happy. So this is a really simple proof of a really simple fact, but I think it's in some sense it's quite lovely, because it says that we can, with just 2 colors, we can make all finite vertices happy in this sense, that, well, at least from every vertex, at least half of edges are good. Okay, and so what to do with such a simple situation? Of course, there can be many variations on this topic, and I will present some of them. One very natural, if you like, list coloring. So one very natural is to look for a list coloring version of the problem. So this is the same problem. The same definitions are kept for good edges, bad edges, and happy vertex and unhappy vertex. But the only difference is that now we have, for every vertex, we have a prescribed list of colors. And for this vertex in a coloring, we can use only colors from its list. But nothing else changes. So we ask ourselves, can we find a majority coloring from any given lists? So in this example, we see that we are choosing some colors from this list of vertices. Some of them are already happy, some maybe not. But you can quickly imagine that the same argument with this switching, but now we switch a color from the list. We have 2 colors in every list, but now this switching operation makes success in the same way. So basically, looking for the list version, nothing difficult, nothing more difficult happens so far. We still have this result, which I attribute to Love, as though he never formulated this result in this fashion. But this is the same argument as he used in his original proof. So I think it's his result. Well, here is another funny version of list coloring that we can also try for this problem. I like to call it maybe color blind version. So this is something like a game. So let me explain it. So we have lists of colors, but there are 2 players. One is this lister who creates this lists, and the other player is painter who is color blind. So the guy who has to color a graph cannot distinguish between colors. So what he sees is only gray vertices. But now this lister reveals one color and says, okay, this color yellow in these lists. And painter must choose in that round which vertices will be colored by this picked color, by lister. And this process is irreversible and it goes on. So another color is presented and the painter must choose some vertices to color vertices. So we see that this is more difficult than just list coloring, because we have to make decisions online in some sense. But well, so the game is won if by painter if at the end all vertices are happy. This very difficult situation, but it still can be proved that from lists of size 2 we can still win this game. And in the terminology of this topic, we say that a graph is paintable if it can be painted by a colorblind painter from lists of size 2. If this is 2, it's 2 paintable. If K, it's K paintable, and of course it can be considered for any type of coloring. Actually, this was firstly considered for usual proper coloring, not for majority coloring. But for majority coloring, we have such a result proved by Lasson, and the proof is also quite easy. I will not show you details, but it's very simple, and also it's very similar to this original argument by Lovas with this switching colors. So you can think of it as a kind of exercise. Okay, so the first variation, I will show you 3 variations on this majority coloring, and the first variation is for digraphs. So it is very natural. Suppose we are given a directed graph, and again we want to color vertices, and some edges will be good, some edges will be bad. Now these edges are directed, but the definition of bad and good is still the same. Good is when the ends are in different colors, and bad is when the edge is monochromatic. But now we change the definition of happiness of a vertex, because we have 2 kinds of neighbors. There are out neighbors and in neighbors, or if we speak about edges, there are edges outgoing from vertex and incoming to vertex. So you can choose whatever, but in a definition, we chose outgoing edges. So a vertex is happy if among outgoing edges from that vertex, there are no less good edges than bad. Okay, so this is quite similar notion, and in the same way we define a majority coloring for a digraph. So this is a coloring where every vertex is happy. This was quite recently introduced by these 5 maybe authors. And in their first paper, they proved that every finite digraph is majority 4 colorable. So as you see, 4 is bigger than 2, so the situation is more complicated for directed graphs. I have a kind of sketch of a proof. It's quite easy argument to explain how to find this 4 coloring for majority coloring of a digraph. But I'm not sure if my sketch will be understood. Okay, so I will explain the picture. So we split every vertex into 2 copies, but it's still one vertex. So we have 2 fragments of our digraph where the edges above are directed to the left and the edges below are directed to the right. So this is a splitting of a vertex into the edges of a digraph are split into two categories, one that go to the left and one that go to the right. And we will color the vertices by a greedy procedure. Firstly, we start from left to right. So we start with the first vertex and we give it any color. Actually, the next vertex is not connected to the previous one, so I still can give it the same color. But here in the third vertex, in the first part of the process, we are looking only on the edges above. So among outgoing edges, there is only one edge to the left. So this vertex must be color blue. Yeah, because if there is only one out neighbor, this majority condition demands that these two vertices must be different color. Here we have two out neighbors, but both are yellow, so we can put blue. It's pretty easy to see that having only two colors, we can always safely choose a proper color. Proper meaning that at most half of the back vertices will be colored in the same color. So we are always choosing a color that is less presented in the out neighborhood. Maybe I do not have such a troublesome situation. Maybe this vertex, it has three out neighbors, blue, blue, and yellow. So I should choose definitely a color yellow, because otherwise there will be two bad edges and only one good. So I chose yellow. And in a second phase of this process, we do exactly the same, but from right to left, and on this lower copy of our digraph. And at the end of this process, we have vertices colored by pairs of colors. Okay, and for every vertex, it must be that its upper copy is happy to the left and the lower copy is happy to the right. So when we glue these colors, we get a color that is a pair of colors, and this vertex is happy on all of its out neighborhood. So this is just a sketch, but the proof is pretty simple and shows that 4 colors are enough for such majority coloring of a digraph. But here is a very intriguing conjecture, as it happens very often in graph coloring problems. So the conjecture asks for proving that actually 3 colors are sufficient. So just one less color than this easy argument, and the problem looks like very difficult. So far, nobody could prove this conjecture. And let me just point that these three colors are optimal value. It is not possible to color every diagram by 3 colors, and this is, for instance, just a directed triangle shows that this bound is optimal, because in this example, every vertex must be colored by a different color. Yeah, by the same argument that the out degree is 1, so it must be every out neighbor must be in a different color. So by this cyclicity, we need to have 3 colors to make every vertex happy. So this is very nice conjecture, and we are trying to prove it, and other people also try to prove it, and so far it is open. But something is known. Looking for the least version. So in the same way, we can define the least version of the problem as in a non-directed case. So I will quickly make this example. We are choosing colors from lists, and some edges are good, some are bad. We want to find such a coloring that every vertex is is happy. And here is our result, which is quite close. This result solves a problem stated in the first paper where this problem was introduced. But you see, this 4 is it's bigger than 3, like in a conjecture of 3 coloring, but it's more difficult because we have this choosability version. But yeah, we still conjecture that this could be improved to lists of size 3. So if this conjecture is true, then of course the previous conjecture is also true. So both are open so far. In this theorem, I show you some chosen facts that were established recently by these authors. So, for instance, if you take a directed graph whose underlying non-directed graph is 6 choosable, so has least chromatic number at most 6. For instance, planar graphs are even 5 choosable. So the class of planar digraphs is connected in this point 1. Okay, so for that type of digraphs, this conjecture is true. Also, for graphs whose dichromatic number is least dichromatic number is at most 3. So dichromatic coloring of a digraph is a coloring in which there are no directed cycles in one color. So if a digraph has such a coloring by at most 3 colors from lists even, then we have this 3 choosability in a majority sense. Here is a quite nice fact. If in a digraph there are no odd directed cycles, then it is even 2 choosable in a majority sense. So this is quite surprising maybe. And one last point says something about graphs of bounded maximum out degree. This is a very interesting paper with all of these results, and there is also another result that I will mention in the next slide. But this fact with these odd directed cycles forced me to state a conjecture that maybe the same is true for kernel perfect digraphs. So I don't know if you know what is a kernel perfect digraph. So a kernel in a digraph is an independent set of vertices such that every vertex outside the kernel is connected by outgoing edge, has an edge pointing to the kernel. And kernel perfect means that not only this digraph has a kernel, but also every induced subgraph has a kernel. And it is a well-known fact that if a directed graph doesn't have odd directed cycles, then it is kernel perfect. So this conjecture, if true, would be a generalization of this nice theorem by these authors. But maybe you can quickly find a counterexample. Okay, and here is a formulation of our theorem that gives this for choosability in a majority sense. And it's, as you see, it's rather complicated, but I will illustrate this theorem on a picture, and we will try to make it understandable. So first of all, we are given our direct. Now, first I will just explain what this theorem says actually. So we are given lists of size 4 at every vertex, but also every color in a list has something which we call a rank. So in every list, every color has its rank, and this rank is just a real number. It can even be a fraction, but it can be even 0 or even a negative number. But the only condition in theorem is that the sums of all ranks of colors in one list must be at least big as twice the out degree of a vertex. So, for instance, for this vertex, we have 4 colors in a list, and here are these ranks. This is just an example. But the out degree of a vertex is, as I can see, 1, 2, 3 edges outgoing. So the out degree is 3. So twice is 6. And the sum of these numbers is actually equal to 6. So the condition is satisfied. But the thesis of a theorem is that if we have these ranks with colors in lists everywhere, we can choose a coloring that satisfies this condition. And this condition says that the number of out neighbors of any vertex in a color of that vertex in this coloring is bounded by the rank of this color. For instance, suppose that our vertex with these ranks is yellow, then the rank of color yellow is 0. So this says that there can be no yellow vertex on the out neighborhood of this vertex. If this vertex is red, then we can see at most one out neighbor in a red color to satisfy this condition. So if the rank is bigger, then we can have more vertices in that color. For instance, the rank is equal to 3, we can even have all vertices in the same color as that vertex, and the condition is satisfied. But then vertex is happy, of course. And it's pretty easy to see that this is stronger than what we want to prove. So the simple consequence of this theorem is that every finite digraph is just for choosable. And we can see it by taking all ranks of colors equal to half of out degree. If every vertex out degree has a rank equal to half of out degree, then satisfying this condition is the same as satisfying the majority condition. And I would like to give you a sketch of the proof, because it's again, it's not very difficult. It's just an induction, but it's not. On the other hand, it's not quite trivial. It's quite interesting, I think. So this is basically it's the argument is by induction on the number of vertices of our digraph, and it goes very similarly to many induction proofs in graph coloring. So we are choosing some fixed vertex, and in this vertex we have 4 colors with ranks. We can order these ranks in a non-increasing fashion, and we declare that in our coloring, because we will delete this vertex in a while, but then we will apply induction, but actually we will use only one of these 2 colors to finish the induction. So we declare it at the beginning. So we focus on 2 colors in a list with the highest ranks. And then when we remove this vertex, we will get a digraph D prime, D minus V, and we have to modify some ranks of colors, but we will modify only ranks of these 2 highest colors. And the modification is just by subtracting 1 from a previous rank in a list of any in-neighbor of a vertex V. So in this picture, we have 2 in-neighbors of our vertex. And if there are these 2 colors actually in the list of these vertices, when we remove this vertex, we need in our new digraph, we need to modify ranks of these 2 colors just by lowering them by 1. And nothing else is changed. We apply induction to this smaller digraph. I hope you see that we are allowed to apply this induction because this modification, the ranks are smaller by 1, but they are smaller just in these in neighbors that has actually smaller out degree, because we delete some edges, and in every such vertex at least one outgoing edge was deleted. So still this condition, this assumption is satisfied. This is important because we can apply induction thanks to it. So suppose we apply induction, we have this good majority coloring in this D prime, and we go back with our vertex with these two colors. And I claim that we can extend the coloring and have satisfaction of condition in this last vertex. And why is it so? It's because these two vertices are of this highest rank. So the sum of all 4 ranks is at least twice the out degree. So the sum of these two highest must be at least the out degree of a vertex. And the out degree of a vertex is, of course, the number of out neighbors. But on the other hand, the number of blue in this coloring among out neighbors of V plus the number of yellow is not bigger than the size of out degree, of course. And this is bounded by the sum of these two ranks. So we have the following situation. We have two numbers. The number of appearances of blue and yellow in the out neighborhood of V is bounded by the sum of ranks of these two colors. The sum of two numbers is at most the sum of two other numbers. So of course, at least one of these numbers must be bounded by the other. And this is exactly the condition we were looking for. So we are choosing that color that satisfies this inequality. For instance, suppose it's blue. So when we choose blue, we have this, and this. If we have this inequality, we choose blue, and we are happy. Okay, so this is the whole sketch of a proof, but maybe even the whole proof. You can think of it, and it's quite easy, but it solves a quite nice problem and makes the conjecture even more intriguing, because again we have a result which is not very difficult for lists of size 4, and we would like to lower them by just 1, and that's maybe very difficult. Okay, so another problem. So here I have an example of a small directed graph, and I want to show you something strange. So first of all, I will demonstrate that in any majority coloring, we need at least 3 colors, because of this degree 1, basically. So if you have only one out neighbor, it must be colored differently. I'm trying to keep just 2 colors, but at some point I need to use the 3rd color. Why I need the 3rd color? Because blue is not okay. Why blue is not okay? Because we'll have on this edge conflict, and yellow is also not okay because these 2 out neighbors are colored yellow. So we need to have 3rd color. So this is a digraph with majority chromatic number equal to 3. But we can think of something which is called fractional coloring. So what is this fractional coloring? Again, I want to explain this on an example. You see now sets or lists of colors. In every list we have 2 colors, but the total number of colors is 5, I guess. It's blue, yellow, green, red, and some kind of violet maybe. So there are 5 in total. But the property of these lists is that actually any coloring from these lists satisfies majority condition. You can try. Maybe I made some mistake, but my intention was to find such an example that choosing any colors from this list, not just one color, any coloring, any colors, if not green, then red, and in any choice we get a majority coloring. So this is something like this fractional coloring. I don't know how it is called. It's well known maybe for the usual proper coloring of graphs. So for instance, a cycle on 5 vertices has the same property that you can, if you have 5 colors in total, you can assign to every vertex 2 colors, and then any coloring will be okay. So this is the definition of majority KM coloring. And so we could even define a fractional majority chromatic number, which is the infimum of such fractions. So on this example, we have this diagram which demands 3 colors in the usual coloring, but now we have our fraction equal to 5/2, because we have 5 colors and size of list are 2. So we have 5/2 coloring. And there is a nice theorem by these authors, which makes a small step towards the conjecture that 3 colors are sufficient, because they at least could prove that there are some, for every finite digraph, you can find some 2 numbers such that our digraph is colorable in this sense, and the fraction of these 2 numbers is slightly smaller than 4. So this is still very far from having 3 colorings, but at least maybe it's a kind of hope that maybe the truth is below 4, at least in this fractional sense. Okay, so now I'm trying to state some problem that maybe it would be nice to study such a fractional version of majority coloring. Now I'm stating some conjecture that maybe this least fractional majority is the same as fractional majority. So these conjectures and these problems are natural analogs of what was studied in the usual traditional proper colorings of graphs, inversions of least fractional, and so on. So the second variation is for hypergraphs. Of course, if you like hypergraphs, then you can think about majority coloring in many different senses. So the basic maybe is that a bad, we have 2 colors, and the bad edge is monochromatic and good is non-monochromatic. And again, vertex is happy if it has more, or at least as many good as bad. So these are analogous definitions of majority coloring for hypergraphs. And actually, again, we are going back to this paper by Lovas, the same argument that we see for undirected graphs with switching colors. The same argument works here in this version, and we have such a theorem. So the proof is just by taking a 2 coloring that maximizes the total number of good edges, but we achieve it by algorithmically, maybe by switching colors on non-happy vertices. Okay, but there are many other types of proper colorings of hypergraphs. So another is that a good edge is when all vertices in that hyperedge are in different colors. So we could call it rainbow. And the bad edge is when even there are just 2 vertices in the same color, so which is non-rainbow. But now, so the definition of happiness is the same accordingly to this definition of what is bad and what is good. But now we do not know too much about it. And again, in a general problem, you can think of any maybe favorite type of coloring for hypergraph and study it in this majority version. It should be easier than in the traditional way. And the last variation, but also quite intriguing, is for infinite graphs. Something very strange happens when we think about this problem for infinite graphs. Actually, it was studied even, or maybe not before LOVAS, but before these directed versions. So the question posed by these authors was whether it is true that we can go with these just two colors for any infinite graph. So the definition is the same. So when we have infinite number of edges incident to vertex, some bad, some good, but the cardinality of good edges should be at least as big as the cardinality of bad edges. So the definition is still the same. And it was proved by Milner and Schelach that every infinite graph is majority three-colorable. So one color more is needed for infinite graphs, but okay, is it needed? Yes, it is needed for some graphs. So they not only proved this upper bound, but they also constructed an example of a graph that cannot be majority two-colorable, but this graph is uncountable. It's quite large. So this causes a natural question whether maybe when we restrict to the smallest infinite graphs, which means countable graphs, so maybe in this class of infinite graphs, two colors are sufficient. And this is quite famous conjecture, quite old, as you see. It is known as unfriendly partition conjecture in another terminology where these vertices have some friends or non-friends. Okay, so we thought about this conjecture and we couldn't prove it, so we stated some stronger conjectures. So, for instance, one natural conjecture is that maybe the same should be true or something similar for this least version. Okay, so of course this one is stronger than this conjecture, which is quite difficult. But actually, it was proved recently that every countable graph is majority three choosable. Okay, so this is now again quite close to the very hard conjecture by just one color. Every time we have these problems with just lowering bounds by one color. And he conjectures in his paper, this author, Haslagrave, that maybe you can get rid of this countability. So maybe you can prove an extension of this result by Milner and Schelach, because they proved that any infinite graph is three-colorable. So he postulates that maybe every infinite graph is three-choosable. But his proof works only for countable case. And we started some investigations of infinite digraphs. Because why not? If this majority coloring is exciting for finite digraphs, then maybe for infinite something interesting happens. So we could prove, for instance, that so this is the same bound as for finite graphs, however, only for countable case. And we state a conjecture that maybe every digraph, maybe every infinite, but every finite, every infinite digraph is majority three choosable. So this is very difficult because it includes not only all infinite graphs, but also all finite graphs actually. In acyclic case, it is also quite strange. So this one of these sketches that I showed you with this bound by 4 colors, where we greedily colored from left to right and from right to left. So this argument shows that if we have a cyclic digraph, all edges are to the left, then 2 colors are sufficient. But in the infinite case, it's again open. Hasselgrave proved bound by 3 in countable acyclic case. And just as the last problem, I would like to mention that we can consider all these problems for hypergraphs. For instance, for uniform hypergraphs, maybe it should be a bit easier to prove something, because if we have large hyperedges, that then we can think that maybe there are more room for making many good edges in our coloring. But this is completely open. Okay, so thank you for your attention. I will stop this place.
Thanks a lot, Jarek, for your happy talk. So I don't know if there is some questions. Yes, thank you. Vinicio say thank you. Nice. I don't know if somebody has another question. The same of Julian. Magda say very nice talk too.
Thank you, Magda.
And okay, if there is not a question by the moment, I have a question. I don't know if it had sense, but I was thinking. Hannah said the same. Had sense, so it's possible to think about the almost happy graph with this. I am thinking about the difference between the good and bad age will be less or equal to 1.
Yeah, it's a good question. It's a good question. Somebody asked me similar questions. I don't remember when it was. So there are many connections. One is maybe that you just say that. You say that. Okay, I can just say that there are some results in different directions. One notion is defective coloring. So, for instance, you say that your coloring is almost proper because you allow that bad edges form a matching in a graph. So this is the same as saying that you allow for each vertex, you allow at most one neighbor in its color. But you can of course try something different, that maybe almost all neighbors are in the same color except one. It should be even easier. So you can play with these parameters, and I believe there are many interesting things that you can get.
Okay, thank you. Julian, yes?
I was wondering if there is this definition about the happy vertex, well, maybe you can define it for another kind of colorings, like the distance related colorings, like L2-1 coloring, where a happy vertex is a vertex that satisfies for most of them. I don't know if there is any.
I can say that you can play with these happiness notions in very different ways. You can take your favorite coloring and consider a majority coloring with this coloring majority condition, but also you can play with this majority condition in different ways, so you can obtain a variety of different problems in this way. Definitely it can be interesting. So for instance, this L2-1 is very popular, and I didn't saw anything about majority version of it. I will think about it now, maybe.
Thank you.
Maybe it's a good idea.
Okay, we have more questions, Juli, or not in face? Okay, Naid.
When you start about the first variation of the majority graphs, you present the last slide of the first part, and you put the example of the 5 cycle with 3 cycle, yeah? And I was thinking of the acyclic diagram, but in the last of the third variation, you talk about the conjecture about this topic. You can explain about this conjecture of the acyclic diagram?
Yes. So the last conjecture was for infinite digraphs, but something which is very easy is for finite acyclic digraphs. So if your digraph is finite and doesn't have directed cycles, you can do majority coloring by using just 2 colors in a very easy way, because you just order vertices in a line. Every vertex has all out neighbors to the left, and you just apply greedy coloring from left to right, always picking a color that is in a non-majority in its out neighborhood. So this is very simple, and now we can ask, is the same true for infinite acyclic digraphs? And we cannot prove it. So it's an open problem. And the difficulty is in it that if you have an infinite digraph, you just cannot have the first vertex that you may start this procedure. For instance, if the order is like on integers, there is no beginning. And I even cannot prove I even cannot prove these 2 colorings, but for acyclic digraphs that has an order of the integers. It's very frustrating.
Thanks.
We have one comment on YouTube from Germán Benítez Bobadillas that he says, thanks for a very interesting talk.
So thank you very much. I'm happy to hear that you like the talk. If somebody wants me to ask of some materials or some other questions, you can write me an email, of course, or anything like that, and I will respond.
Okay,
I can send slides, of course, if you wish, and so on.
Okay, thank you. So I think if we receive more questions by Facebook, we send you later. So thank you very much for your nice talk. And we have 5 minutes for the next talk. Okay, thank you very much.